Hello, everyone, and welcome back to the online Digging Deeper series. I'm Amy David with the Friends of the Sawtooth Avalanche Center. And tonight we have avalanche specialist from the Avi Center, Ethan Davis, to let us know where the heck the snow is. He's going to discuss the weather factors that shape our winter season. And before we turn it over to Ethan, I'd like to send a huge thank you to everyone on behalf of the Friends of the Sawtooth Avalanche Center who contributed to the Giving Tuesday campaign that we just finished up yesterday. We really appreciate all of your contributions. And if you'd like to donate in the future, you can do so on our Venmo account at sawtooth-avalanche or on the website. And we hope to see many familiar and new faces at the 5th annual Homegrown Film Festival that's coming up this Saturday, December 4th. And you can find out more info on that at Sawtooth Avi or after this presentation. But we want to get right into the good stuff with Ethan. So first, I'd like to introduce our virtual host from the Elephant's Perch. For years, the Elephant's Perch has hosted the Avalanche Center events, and we're all looking forward to the day that we get to do these in person again. But for now, we're going to stick with the online program. And tonight, we're grateful to have the Elephant's Perch as a virtual host again. And we invited Kate to share a few words on behalf of the Perch. So go for it, Kate.
Hi, everyone. Thanks for attending another year of Digging Deeper. It's just been a really great series, and the Perch is super stoked to be a sponsor of the Sawtooth Avalanche Center. And I'll be quick and short. We're hoping for snow, so I'd like you all to talk to the snow gods, but maybe starting Monday, we'll get to see some, especially up in the Stanley Valley. And don't forget to come into the Perch and shop for your Avi gear. We've got hats, we've got a lot of goodies, and 100% of the proceeds go back to the Avalanche Center, and they make great stocking stuffers and Christmas gifts. So we hope to see you in the Perch soon, and we hope to see you even sooner out on the slope somewhere. Have a great holiday season. Thanks for attending.
Awesome. Thank you so much, Kate. And thanks to everyone at the Perch. We greatly appreciate what you do for the community. And tonight, everyone who's watching the presentation, you can comment and ask questions during Ethan's presentation in the Q&A box, which is at the bottom of your screen, or you can hit the raise hand button, also at the bottom of your screen, and then I can unmute you and you can ask the question live, which will make it a little more interactive and fun. So be sure to fire away all the questions or comments you have. And we will now turn it over to Ethan, our in-house weather specialist.
All right, thank you, Amy, and thanks, Kate. We really appreciate the support from the Elephant's Perch and the Friends of the Avalanche Center. We're going to dive right in because I tried to pack a lot of information into this short hour presentation, and I want to leave a little bit of time for some questions at the end. But like Amy mentioned, if you have questions as we're going through, don't hesitate to interrupt, and Amy will let me know and we can answer them as we go. So we'll jump right in. We're going to be talking a little bit about current conditions. We're going to look at the Climate Prediction Center's official winter outlook, which they update once a month. You'll see that outlook is heavily influenced by El Nino or La Nina, given the year, which is also known as ENSO, which we'll touch on kind of third there. Then we're going to move into atmospheric rivers, which I'd like to highlight as a weather phenomena that if it's not on your radar, being in the inland Northwest as we are, it needs to be on your radar, and we'll talk about their importance as they shape our winter snowpack. And then we'll offer some parting thoughts and answer your questions. So what do things look like out there right now? This is snow depth as of yesterday. You can see it's pretty thin down in the lower elevation sites, 1 to 4 inches kind of over in the Soldier Mountains. Obviously, if you're in the Wood River Valley watching this presentation, you know that there's not very much snow here in the Wood River Valley, and we normally do have snow down low this time of year. But notice if you look up at Galena Summit, which is this area up here, we've got anywhere from 1 to almost 2 feet of snow, kind of at Galena Summit and just over into the headwaters in Vienna. So we do have a decent amount of snow up high. Those percentages as of yesterday, percentage of normal rather, you can see that those areas that have that 1 to 2 feet of snow have anywhere from 100 to 120% of the annual expected snowpack for this time of year. So it's actually a little bit better than you might think if you're down here in the dry Wood River Valley or down in Boise area. But as I mentioned before, as you kind of move down to lower elevations, that snowfall really drops off quickly, and we're well below normal in parts of the Little Wood, the Big Wood, and over in the Soldiers. And a big reason for that is that first storm we had in October had a rain line where primarily 8,000 feet and below, a lot of that precipitation that fell was in the form of rain. Some of it did fall as snow, but a lot of it fell as rain. And above about 8,000 feet, the majority of that precipitation fell as snow. And so it's still kind of hanging on up there. So the official climate outlooks from the Climate Prediction Center is something that you guys are probably all pretty familiar with when you see these sorts of graphs. We're going to talk a little bit about what they mean, how they're created, and what it actually means for us here in Idaho. The first one we'll look at is the seasonal temperature outlook. I put a star there, generally centered over our forecast area at the Sawtooth Avalanche Center. And you can see that we just barely fall into that first shading of blue. And if you read down at that scale right here, that means that we are leaning toward a colder winter. So a 33 to 40% chance of having a cooler winter season this year. And again, this outlook is a 3-month outlook. So it's looking anywhere across the 3 months of January, February, and March. And these forecasts or these outlooks rather are issued once a month. So this one was issued on November 18th, which is the most recent one that we can pull from. Another way to look at it is that we have a 66 to a 73% chance of near to below normal temperatures. So there's a decent chance that we'll be cool, potentially a little bit colder than normal, according to this outlook. Areas that these sorts of plots really start to shine are up in the Pacific Northwest and down anywhere from Texas to the Florida Panhandle, which have a bit more certainty associated with them. So if you're down in Texas or the Gulf Coast, you can expect that you have a greater than 50% chance of it being a warmer than normal winter. And up in the Pacific Northwest, we have roughly a 40% chance to be cooler than normal. Overall, these temperature graphs generally kind of have limited predictive help for us here in Idaho. Moving along to the precip, which is I think what most people are interested in when they're looking at these plots, at least if you're an outdoor winter recreator. And we fall right in this white area. So what does equal chances mean when you actually see this? Well, it means that we have a equal chance of being above normal precip, near normal precip, or below normal precip. So essentially it says that we have equal chances of getting any 3 of those outcomes. So essentially it unfortunately it has no predictive help. If you are further north though, up into the Panhandle, you have a 40 to 50% chance to have above normal precipitation. And the desert Southwest has a 40 to 50% chance to have below normal precipitation. Unfortunately for us though, we kind of fall right into this area right in the middle. I can say from experience though that every La Nina is different, and La Ninas are going to influence the forecast area across our zone differently up north, like in the Banner area, than they do in the Wood River Valley. And sometimes that can be a pretty stark contrast, even given just the short distance right there, especially since we kind of lie on this threshold where it changes from potentially getting missed by storms down here or getting clipped by northwesterly storms that hit the Banner Summit area. So again, we have essentially no predictive help, unfortunately, from these CPC outlooks for precipitation. And the reason I showed these is because these seem to be, that kind of ends up being the end of the story for a lot of people. They're like, well, I looked and we're going to get slightly above, precip and near normal temperatures. And they just kind of take that as the gospel. But I think having a little bit better understanding of how the CPC comes up with these we'll give you a little bit more knowledge to arm yourself with what they actually mean and what their limitations are. And then I'll offer potentially something that's maybe a little bit more helpful to look at rather than these 3-month outlooks. So how are these outlooks created? The recipe for the outlook, kind of similar. I'll use the analogy of your grandmother's cookies. The basic ingredients from batch to batch are the same, but there's something special that through experience, either the CPC or your grandmother can tweak the final ingredients to come up with the final product. So when we're talking about the base ingredients of this 3-month outlook, the January, February, March outlook, the bulk of it is the El Nino Southern Oscillation, which we'll just refer to as ENSO from here on out. And ENSO, otherwise known as La Nina or El Nino, accounts for 40 to 60% of the observed variability in our winter weather. That's more accurate in certain places of North America, as we'll find out, than it is in Idaho. But the bulk of these outlooks are leaning on whether it's a La Nina year or an El Nino year, and then using what we know about those weather patterns to create this 3-month outlook. The other pieces, the kind of interchangeable pieces that are used in these forecasts, are pretty varied. There's ocean and atmospheric models, there's ensemble models. They look at historical soil moisture because, as we'll talk about a little bit, the air gets its moisture from the soil and from the ocean. So where there's a lot of standing water near the surface or a lot of soil moisture, that can create storms. Similarly, warmer water in the oceans can create storms. So historical sea surface temperatures are important, and also just climate normals over a long period of record can inform forecasters. But again, it's hard to bake cookies with only 40 to 60% of the ingredients. So you really need to factor in that there are all these other things going on, and that's where the experts at the CPC put their skills to the test. So because El Nino Southern Oscillation, or ENSO, is the bulk of this of these forecasts, we'll focus on what ENSO is to give us a little bit more knowledge in that realm. Although the CPC's outlook may not be particularly helpful this year, there are some predictable weather patterns that arise with both La Nina and El Nino winters. And it seems to me that people often have an idea of what they expect the weather to be with a La Nina or an El Nino, but very few can actually describe what it is. So in this next section, we'll dive down a little bit deeper, or dig deeper, as it were. So ENSO has 3 phases. We have El Nino, which is the warm phase, neutral, which is just a kind of an average phase, and then La Nina. ENSO is a linked atmospheric and ocean phenomena that predictably affects weather across the globe. So ENSO shifts irregularly back and forth between El Nino and La Nina every 2 to 7 years. And if you've been paying attention recently, we've been in the colder phase, or the La Nina phase, of recent years. Each phase triggers predictable disruptions in temperature, precip, and wind, and those changes modify large-scale air movements in the tropics, which has global side effects, which is pretty wild. So as I mentioned, it's a linked phenomena. It's between the ocean and the weather. So the first thing we'll focus on is what it looks like in the oceans. The top image here is sea surface temperatures, or departures from normal sea surface temperatures. So when sea surface temperatures over the central and eastern Pacific over the equator are cooler than normal, that's said to be a signal of La Nina, an ocean signal of La Nina. When those same areas in the central and eastern Pacific are warmer than normal, that's said to be an El Nino signal. This is a composite image of what it looked like in November over this same region. So we're looking kind of here right along the equator, and you can see these blue colors indicate cooler than normal temperatures. So we'd expect a La Nina to be present. And how do we know if a La Nina is present? We can't just look at it and take a good guess. What they do is they put a little box around an area between 120 west and 170 degrees west. And this is called the Nino 3.4 region. There's a couple other regions that they like to focus on for different climate indicators, but this is one of the main ones for determining whether the ocean is in a La Nina state or not. And in that little box, they average out those sea surface temperatures. And if it's greater than a ½ degree departure from normal, cooler, then it's La Nina. If it's greater than a ½ degree warmer, departure from normal, then it's an El Nino or a warm phase. Right now, we're in the midst of a moderate strength La Nina, and the CPC is giving a 90% chance for this to continue through the northern hemispheric winter of 21-22, and a 50% chance to continue into the spring. I should mention that I imagine I'll get a question about the difference between a weak, moderate, and a strong La Nina. A weak La Nina is anywhere from a ½ degree to almost a degree departure cooler. Moderate goes from a degree to a degree and a half, and then strong is greater than 1.4 degrees C departure from normal, cooler than normal. So that was our ocean signal. Now, what does that ocean signal do? And how does the atmosphere link up with it? So what's the atmospheric signal, and what kind of weather can we expect from a La Nina? Well, you can see the ocean signal kind of underlaid on this image here, where this blue is the cooler pool of water in the central and eastern Pacific. And cool water, if you just had 2 cups of water sitting out in front of you, if one was warmer than the other, the warm cup of water is going to have a whole lot more water vapor coming in and out off the surface of the water. So that water vapor that's coming off of the warm cup in front of you, you can kind of imagine as this warm pool of water over Indonesia over here. And with more water vapor available, it's going to be available to produce tropical thunderstorms. So there will be unstable air that's going to be rising in this big column of thunderstorms here over Indonesia. Of course, if that happens, we expect there to be more rain over Indonesia in that area. With that rising motion, we're going to get an increase in trade winds. So as this wind is rising, it's kind of sucking air in from both sides, which is going to increase the trade winds along the equator, which has a kind of an interesting positive feedback loop effect of pooling more water that's warm here, because as the wind blows across the surface, it's going to be blowing all the warm water along the surface and pooling it over here in Indonesia. And as that water moves from the surface here to Indonesia, there will be upwelling of cooler water coming up into this region over here in the central and eastern Pacific. Cool water tends to suppress storm activity. So we're going to have sinking air motion here over just off the coast of California and Central America, which is going to create kind of a high pressure system or a blocking high pressure system that tends to push the jet stream to our north. So just that one fact of moving warm air, or warm water rather, excuse me, from one portion of the equator to another has global ramifications in weather, which is pretty phenomenal in my opinion. So as we mentioned, we're going to have a bunch of thunderstorms here over Indonesia. So of course it's going to be wetter. Wetter than normal conditions also tend to be observed over northern South America, southern Africa, and the Pacific Northwest. La Nina also contributes to abnormally cool conditions across much of the globe, most notably over southeastern Africa, Japan, southern Alaska, and the west central Canada. So if you grew up in the Pacific Northwest, like I did in Oregon, when you hear La Nina in Oregon, you usually think cool and wet. And the odds that happens in Oregon, Washington, and BC are actually pretty high. And you can see that marker shown here. And now I don't know anybody from Florida, but I imagine if they hear La Nina, they probably think dry and warm, because the odds are pretty high down in this area that they're going to experience a dry and warm winter. Zooming in a little, remember that sinking air that I showed you a couple slides ago, that over that cool pool of water here off of the coast, that's going to create this blocking high pressure, and that blocking high pressure is going to push the jet stream further to the north. That jet stream is then going to dive down somewhere. This is an average position of the jet stream. Of course, it changes day to day and throughout the winter, but this is an average position of the jet stream during a La Nina winter. Jet streams are a good indicator of kind of a dividing line between cooler, drier air to the north and warmer and wetter air to the south. So you can see that cold air. And the reason that we see colder than normal temperatures generally in our neck of the woods for a La Nina. And then the storm track is going to follow the jet stream as it comes down through here. So a little dip in the jet to the south can be pretty favorable for us. If it moves to the north, we can be high and dry. So again, that's kind of part of the reason why we end up right on the dividing line here with La Nina winters, and also in the CPC outlooks quite often. If we think back to those CPC weather outlooks, remember these outlooks are heavily influenced by the fact that it's a La Nina winter. In fact, half of these plots or half of the variability in our winter weather, roughly, that influences those graphs on the right comes from the fact that it's a La Nina winter. And there are a lot of similarities, as we just mentioned. Wetter and cooler is expected in La Nina, so you see that below normal temperatures and above normal precip in the Pacific Northwest. Similarly, drier and warmer around Florida, below seasonal precipitation in Florida, above temperatures in Florida. So the La Nina and El Nino do have large influences on these outlooks. Looking a little bit more locally, I'm just going to highlight a couple of these to kind of cut through some of the noise here, but this is precipitation across the United States, and all of these are different La Nina winters. The cooler colors that you see are going to be departures from average precipitation in the positive realm, so more precipitation, and darker browns are drier years. The ones that I outlined in blue there are the only two drier winters that we had from this data set, which was between 1981 and 2010. So back in 49-50, we had a La Nina that was drier than normal. And down here in 84-85, we had a La Nina that was drier than normal. Of course, if this data set included last year, we'd have a pretty dark brown box here as well, because we had a very, very dry winter, especially given a La Nina season. But the good news is 9 out of these 11 through this data set show wetter than normal years for La Nina, which is good for us. If we take a composite average over this entire data set, so this is from 1950 through 2009, and we're looking at strong La Nina winters, blue colors indicate winters that had more than average snowfall, and brown is less than average snowfall. And good news for Idaho, at least with strong La Nina winters, is that we can get anywhere of up to a foot more snow on average during a La Nina winter. Again, though, these were strong La Ninas. Right now we're in a moderate, and that signal tends to be a little bit weaker for a moderate La Nina. Another way to think about it is how much snow do we still have on April 1st? So how deep is the snow in April? And for a given La Nina winter, we tend to have anywhere from 130 to 150% of our normal average snowpack on April 1st. So 50% more snow on April 1st than we would on an average winter, which is quite substantial actually. Drilling down just into the Bigwood Basin, this plot right here, you can kind of think of as snow depth over the course of the year. So on the left-hand side, we have beginning of the fall and then out into July if we still have snow. And this is actually snow water equivalent. If you guys are familiar with that, you can think of it in that regard, or how much water essentially is sitting out there. But you can also think about it as snow depth, and that'll work pretty fine for you. And the lines that I have on here, the upper line is the historic maximum snow water equivalent, or roughly analogous to snow depth. And then this one down here on the bottom is the least amount of water we have sitting out there over our course of record. And the first line I want you to look at is this green line. That'll give you a reference for what the average is. So the average kind of comes up through here in the middle. The second line I'll have you look at is the black line, and the black line is us right now. So the winter of 21-22. And we started off fairly dry. We had that big storm in October that I talked about earlier. And I'm sure if you guys were around the Bigwood Valley, you noticed the just kind of torrential rains down low and heavy snows up high. And that actually bumped us up to near record snow levels for that time of the year. And since then, we've been mostly dry with the exception of just a couple small storms, and we've come all the way back down to average. Like I mentioned before, it's not quite as bad as a lot of people think, even though it's really dry down here. If you look at the basin as an average, which includes the upper elevations, we're still kind of right on par with an average winter. The other two lines I threw on there just for reference are our last La Nina winters, or the other three lines are our last La Nina winters prior to that. So 2021, last winter, if you're around here, was extremely dry. We had an early season storm, which kind of upticked there. We had a long dry spell, which created a lasting weak layer that we dealt with for the majority of the year. And then we were kind of on an average slope there for a while, and then it just petered out entirely in the spring. We just had a really dry spring and summer. In fact, almost record low for the basin as we were approaching this red line down in here. 2018 and 2012 were the other La Nina winters prior to that, and they kind of followed a similar average snowpack, but had big wet springs, so they ended up being a bit above normal snowfall years, but then kind of tailed off pretty quickly. Looking at that same sort of plot, but now we're looking on the other side of Galena Summit for the upper Salmon, so the headwaters of the Salmon, Stanley Basin area. And we actually did hit record snow levels this year for that first October storm. And it's slowly melted and brought us roughly back to average. Otherwise, the lines kind of were similar to the Bigwood Basin on this side. One thing I will note that I alluded to earlier is that sometimes La Nina winters do just, if you're paying attention every day like we are at the Avalanche Center, you just notice that even if it's dry down here, an occasional kind of northwest storm will come and give a little bit more precipitation to the Salmon side of the pass. And you can tell that on those two winters in particular, 12 and 18, we kind of rode that average line a little bit more closely than we did when we were looking at those same two lines, which were pretty dry and below average for most of the year on the Bigwood side. This graph here is probably my favorite way to look at all of the last 60 years of ENSO phase data and compare it to total basin-wide snowfall. So I have to give a big shout out to Mike Houston here from the Pocatello National Weather Service, who assembled this data and is helping me interpret it. And so what he's done here is he's put all of the different years across the bottom. So each bar represents a year. The height of the bar represents how much snowfall we got in the basin. And this is the Bigwood Basin now above Haley on April 1st, about how much snow we had there on April 1st. So this dashed line in the middle is an average year. And the color coding is red for El Nino and blue for La Nina, and the gray is neutral. So hopefully that's clear to everybody. When you're looking at the blue bars, you're looking at La Nina winters. The red bars are El Nino winters, and the gray bars are neutral phase winters. And we'll kind of step through some of the last 10 years here really quickly. Again, when we're looking at it on a historical context, last year, which was a La Nina year, falls way down here in the lower quartile of this plot, which was pretty sad. In fact, it was the second driest La Nina winter that we've seen in the Bigwood Valley on record. Moving forward to winter of 17-18, and we were kind of slightly below normal. 11-12, we were slightly above. 10-11, we were near normal. 8-9, we were a little bit below. 7-8, we were near normal. And you can see that in those 10 years, most of our winters kind of fell just one side or the other of pretty much average for snowfall. And those are the last 10 years worth of data. Although the last 10 years or so are clustered near normal, if you kind of just take a big picture view and look at all the blue bars, there is an overall prevalence of blue bars that sneak out onto the right or the wetter side of average. So there is a clustering, a little bit more of blue on this side of the graph, as opposed to drier years, which would be over here. We would be, I don't think anyone's going to be forgetting this winter anytime soon. If you were in the area, that was winter of 16-17, which was record setting for a lot of areas. It was a neutral year, but that February just absolutely dumped on us. And this is a picture out Croix Canyon with my wife snowboarding down off Della, the north side of Della there. And that sort of coverage, we were looking down at the old animal shelter there, if you're familiar with the Croix Canyon just west of Haley. That sort of coverage we really haven't seen since. And, it was just an absolute monster of a year with snowfall. And, 2 of the top 4 were neutral years. I think a lot of people don't really talk about when they're talking about La Nina or El Nino. They kind of forget about the neutral phases, which do have a potential to deliver. This was just looking out my front window in February, and it kind of pushed all the moose out of the draper that normally hang around right into the neighborhoods, and they just pretty much never left all winter, just hanging out on the roads because they were having trouble walking around through the snow. Breaking it into just wet and dry years, you can see dry years are dominated actually by neutral phase ENSO, shortly in second place by El Nino. So we're generally drier on neutral and El Nino, but La Nina, which we're in again now, remember, moderate La Nina, trends towards the wetter years, with 13 and a half of those years wetter, and followed shortly or closely behind actually by El Nino. But most of our La Ninas end up on this side of the graph. There are some limitations, however, which we'll go through. It's obvious that ENSO phase has some predictive value for our winter outlook, but as you saw in the CPC outlook, it's not always an obvious answer. And remember that it's only roughly half the picture. So here are some of the main limitations of using La Nina and El Nino to predict winters. First is that it has pretty small predictive skill over Idaho. We often end up in the man's land where we have equal chances of above, below, or normal precip and temperature. And that's particularly true with weak El Ninos and weak La Nina events. And so may not develop as forecast. Remember, it is a forecast, so those are subject to error. And El Nino, or if, an El Nino winter can turn into a neutral, during the winter. And if the forecasters miss that, then that might affect their outlooks. We also have a short period of record, since 1950, which we have good records back till, there's only been about 25 years of La Nina data. And then those are subclassified into a few strong, 5 as moderate, and 12 as weak. So you have smaller and smaller categories, and your sample size is so small that it's hard to draw real concrete conclusions when, climatologically speaking, you like to have at least 30 years worth of records to really start to say something with any confidence. So another challenge, obviously, that we have is a changing climate. So what we looked at, pre-1990 with La Nina patterns is starting to look very different than what we see post-1990 for La Nina patterns. And I chose 1990 as a rough number there, but it is changing quickly. And so we're kind of losing that same backdrop that we can trust. It's changing every year. The presence or absence of 1 or 2 big storms can really define the season. So ENSO is great, but one big storm here or there can make all the difference. And that's really what I want to focus on for the next section, and leads me into our next little short topic, which is going to be atmospheric rivers. So ENSO's great and all, but when you really want to know when it's going to snow and the big events that really shape our season, we need to be talking about atmospheric rivers. If you grew up on the west side of the Cascades or west side of the Sierra, you've probably been hearing about atmospheric rivers your whole life. Inland from those mountain ranges, though, on the east side, I think they've been overlooked, kind of chronically overlooked for a number of years, and they're just starting to be more understood as to their importance of our winter snowpack. An atmospheric river is a relatively long, narrow region in the atmosphere that's kind of likened to a river in the sky, hence atmospheric rivers, that transport the majority of the water vapor from the tropics down along the equator into northern reaches like where we live here in Idaho. So atmospheric rivers are actually the largest, quote, rivers of fresh water on Earth at any given time, transporting on average more than double the flow of the Amazon River. So when an atmospheric river makes landfall, this moisture is really condensed down into the lower portion of the atmosphere. So when it impacts a mountain range, that just gets pushed up, and that creates just heavy rainfall and snow on those first any sort of topographical barrier. So this animation here shows precipitable water. The wettest places are depicted in warm colors, which is generally over the tropics. And as you can see, this water vapor is kind of getting swept from east to west along the trade winds here. And then this little arm that extends out right here is an atmospheric river. Okay? And that's impacting California right there. If you look at a global animation, and this animation was actually just taken from middle of November, you can see there's these long filaments of water vapor getting stretched out from the tropics, which are really pretty beautiful images here. But this one is one of those that you've probably been hearing about lately since in the last month or so, or at least the last few weeks, that have just been pummeling BC, Vancouver, Washington, and Oregon. This one was on the 14th of November. And you can see it again, kind of stretch up right here and then kind of sweep down the coast. These atmospheric rivers are often associated with extratropical cyclones or low pressure storms that kind of sweep down and then kind of draw in that moisture from the tropics. They have a scale similar to a hurricane scale in the sense that it's kind of a 5-category scale, but there are some main differences that I think are kind of interesting. So the hurricane scale is based on just intensity. So if an atmospheric river scale was based on intensity, it would just be literally how much water is moving past a given point, and how fast. But what's interesting is that the atmospheric river scale also takes in duration into account. If you think on the hurricane side, if you have a category 3 hurricane, which might not be as strong of a storm, but it just parks itself in one position, you can get big storm surges, lots of flooding, and just consistent rain in one place, which has a very large impact. So it could be a very devastating storm. But then again, if you just had a category 5, it might just sweep by you really fast, and yeah, it could knock some things down, but the overall impact might be less than a category 3. So with an atmospheric river scale, they're kind of just looking at the end effect. Is it beneficial, meaning we refill some reservoirs, we get a little bit of water for our plants, or is it primarily hazardous, which is just flooding and landslides or avalanches and so forth? So if we think of the same storm, but one that's propagating and one that's not, you can imagine how one that's stationary, like this one on the left, can just bring extreme flooding to coastal BC here, while the other one on the right, which might only linger for a short period of time over coastal BC, but then propagate downward, might have less of an effect. So bringing it home to Idaho, there's a paper that's really interesting by Rutz et al. In 2014. And they started to look at inland penetrating atmospheric rivers, the ones that make it past the Cascades, past the Sierra Nevada, and what were their effects on inland precipitation. And there's two really big findings that came out of that study for our area. The first is that roughly a quarter of our winter precipitation is due to atmospheric river events, which is pretty phenomenal. The second is anywhere from 25 to 55% of our biggest storms are fueled by atmospheric river events. So they looked at our upper 10% of our largest storms each year in our region, and they were able to trace those storms back to atmospheric rivers at least a third to almost half the time. So when we're talking about the storms that really have the biggest impacts on our weather in the wintertime, we're talking most of the time, we're talking about an atmospheric river fueled event. And a substantial portion of our winter precipitation comes from those events as well. This satellite loop shows that storm that I've been talking about from October. And you can see, as I mentioned before, that a lot of times these atmospheric rivers form just in front of the warm front of a low pressure system or an extratropical cyclone right here, which is a big low pressure system. And then you'll see some rapid intensification and a draw of moisture up from the southwest here. I'll show you. This hit us on the night of the 24th or midday on the 24th, starting right about now. We're right here. And this is just drawing moisture in from that moisture-rich region of the tropics, and it hit us for about 24 hours and essentially gave us an instant snowpack. So we had an atmospheric river already once this year that gave us our biggest storm, and just another example of how impactful they can be. This is just an image that shows the center of that cyclone and the location of where the atmospheric river was right here. And its primary impact was California here, where it was classified as a AR4 or AR5, given different locations to look at. And they got over 10 inches of rain in some of Northern California mountains, which is like 4 of our biggest storms kind of combined pretty much over the winter. So what sort of effect did that have? You can see it right here. So our snowpack was relatively shallow, and then we had this really big bump in overall snow water equivalent. This is up at Galena Summit, and it bumped us right into record territory. I'll give you one more example for why atmospheric rivers are so important, and it harkens back to the winter of February of 2019. These images that I'll show you on the right-hand side are from the Center for Western Weather and Water Extremes, which I'll provide a link for at the end of the talk. And I highly recommend, if you're interested in atmospheric rivers and forecasting them, to take a look at their website. It's really, really cool stuff. So on the left here, we have the biggest storms of that month, February of 2019. And then on the right, we have this report from the Western Weather and Water Extremes that shows the dates of landfalling atmospheric rivers. And a few years ago, I wanted to just try to see, like, did those correlate with our biggest storms? And turns out they did. So our first big storm of that month was February 2nd through 5th. And what you see here is a landfalling atmospheric river on February 1st. And remember, it takes roughly 24 hours, sometimes 18 hours, sometimes 36 hours. It depends on the track of the storm to reach us here in Idaho. Our next big storm was the 12th through the 16th, and we had a landfalling atmospheric river on February 12th. And then our biggest storm of that month was February 23rd through the 28th, where several inches of snow water equivalent fell in the Big Wood River Valley. And that was due to 2 landfalling atmospheric rivers on February 26th and February 27th. The shading on this is actually very interesting to look at too, because the really, really bright colors that you see here are the area are correlated to high precipitation values. And you can see the obvious places that got a lot of precip out of these atmospheric rivers, which are the Cascades and then down into the Sierra. But then you look on the east side of that and it turns blue pretty much everywhere except for us and the Tetons. And so it's pretty remarkable that we're this little island here that just happened to get hit by these 4 landfalling atmospheric rivers. And that's not a coincidence, because if we are going to get moisture out of an atmospheric river, the sweet spot for them to hang out is roughly from this kind of little bump in California sticking out here to Central Oregon. If an atmospheric river can sneak through this little window, that has the clearest path with the least amount of mountains to impact us. Oftentimes, though, they kind of bend and come from the south, and that kind of southerly flow does have a better impact for the Wood River Valley, as we do better on storms that come from the south. So anywhere in this region roughly, but particularly along the California-Oregon border, is where we really benefit from an atmospheric river. So now we're looking at that same plot that we've been looking at previously, except it's for the winter that I'm talking about here of 2018-19. So 2018-19 is this darker green color. The average, again, is this bright green color. And you can see that we were really hurting. It was a really, really dry early season for us there until February. So there's that February 2nd through 5th storm, which was a big bump. There's that February 12th through 16th storm. And then there's the February 23rd through 28th storm, which is the biggest of them all. And it just, I think it's really remarkable that one storm can bring us from well below average to average. Another one can bring us to above average. And then another one can bring us to well above average. So again, these atmospheric rivers are kind of like the building blocks of our winter snowpack. Looking at the percent of normal of snowpack before that February, we were, as I mentioned, really hurting in the 50s and 60s percent of normal. And then at the end of that month, we jumped all the way from 50% of normal to 150% in some areas, even 200% of normal down in the southern mountains, like Soldier down here, 196% of normal, and it was 77% of normal prior to those storms. Of course, that much snow brings avalanches with it. Between the nights of the 25th of February and the 26th, 2 homes and a railroad bridge were damaged by avalanches near Greenhorn Fire Station, which is just south of Ketchum, a few miles. During that same period, a slide also impacted a home on the north side of Dollar Mountain. This is down by the fire station there. The snow had to go down into the river canyon and come up. It's a very steep bank on the other side, and kind of crashed in through the French doors here and into their home. And they were home. There were trees in their hallway and trees up on the roof of this house, and we went to go check it out. So obviously, atmospheric rivers have big impacts on our area. So we'll take it home with some takeaways here. La Niñas are generally good for snow in the Wood River Valley. I think that's about as far out on that limb as you want to say. So when we're talking La Nina, you can say, yeah, on average, we're either near or slightly above normal. I wouldn't look into it too much further than that. But atmospheric rivers, on the other hand, are of huge importance, essentially providing the building blocks of our winter snowpack. So take note when you hear about them in the forecast. And here is that link if you guys want to take a screenshot of that link. You can check out the atmospheric river forecasts. They run live weather models just for that. It's a pretty fascinating website to check out. So if you want to look ahead, I would kind of ditch the 3-month outlook. Sorry to say, but they just really aren't very helpful unless you're in the Pacific Northwest. If you're here in Idaho, I'd focus more on the 8 to 14 day forecast, because 8 to 14 days offers those forecasters so many more tools with weather and ocean phenomena that are more fast to develop, that they can't really use in those 3-month outlooks. So check out the CPC's website for the 8 to 14 day outlooks, because if you're looking for an extended kind of, is it going to be warm and wet, or is it going to be cool and dry? Like, what are we looking for? They have those similar sorts of plots for that time period. So hopefully I've been able to show you a bit of what goes into those CPC weather, winter weather outlooks, and I've armed you with a bit better understanding of some major weather phenomena like La Nina, to better understand La Nina, as well as atmospheric rivers that affect our winter weather here in the Wood River Valley. And with that, I'll gladly take any questions that you folks have. Thank you.
That was great. Thanks, Ethan. For anyone that has questions, again, you can type those into the Q&A box at the bottom of the screen or tap the raise hand button and we can unmute you and ask live. While people are typing their questions, Ethan, I was hoping I could get your insight on if there's any difference with how the atmospheric rivers may, land, or the amount of snowfall based on if you're located south or north of Galena Pass, just if that flow gets split or how that works.
Yeah, there's kind of an interesting slide I think I have. I'll see if I can find it at the end of my presentation here. That shows the importance of where the landfalling atmospheric river actually makes landfall. So here it is. So generally speaking, you want to be, if we're going to get impacted here, what I should say is these arrows are the general pathways that are favorable for atmospheric rivers to take. So the pathway that's most likely to affect our region, again, are ones that make landfall right here at kind of the Oregon-California border. So atmospheric rivers are going to be more influential for the southern and western mountains, so Western Smokies and South Valley, than they are going to be for north of Galena Pass. And the main reason is that a lot of the ones that kind of trend up toward that way kind of miss us to the north. And the ones that do make it to us, again, because of this barrier of the Cascades, a lot of them that do make it to us are going to be approaching from the southwest and from the south. And if you think back to some of the big atmospheric river events that we've had in the past, there can be more snow oftentimes in Haley than there is at Baldy, and more snow at Baldy than there is at Galena Pass, if it's a true kind of southwesterly flow, which a lot of times the atmospheric rivers are. Like those ones of those avalanches that I showed earlier were pretty heavily favored for Galena Summit and south. That's not to say that it won't bring a decent amount of precipitation to the mountains in the Sawtooths, but they're primarily focused on the Western Smokies and the Southern Mountains.
All right, well, we've got a question for you in the chat box here. So from Doug, the big 50-inch storm last year, was that a river?
I have to say yes, it was. I didn't look specifically at that one to see whether it was classified as an atmospheric river or not, but it almost had to be. I mean, given the amount of precip intensity, particularly, like I mentioned, that it was just absolutely dumping down here in Baldy and was doing not very much north of the pass. So that's a pretty good signature that it was an atmospheric river. Yeah.
All right, now we'll just keep firing away at you. So Travis has got a question, and that's, how far inland can we observe measurable effects of atmospheric rivers?
I have a pretty good slide for that one too. So this was a study done by Hatchett et al. In 2017. And the one that we kind of want to look at here, the colors, it's a pretty complex figure. The darker colors show the amount of the percentage of the winter precipitation that they get each year due to atmospheric rivers. So again, I said we get roughly a quarter. So Idaho falls in this color. If you look at the coloring is what you're looking at. So this light greenish color. So we get, 25% of our precipitation here. If you
Oh, Ethan, I think your audio cut out just a little bit. If you want to adjust that mic.
Oh yeah, is that better?
Yeah, that's a lot better. We
Okay,
just missed the last 30 seconds.
okay. So that kind of harkens back to this slide. Roughly 25% of our cool season precip is due to atmospheric rivers. So this blue, but you can see beyond us, this dark blue color here in Montana, you're looking at like less than 15%, almost down to zero. So when an atmospheric river comes inland, and it sneaks through Northern California and Southern Oregon, really the last remnants of that moisture get kind of drained out by the Western Smokies here and the Wood River Valley. And by the time you get to the other side of our mountains, it's pretty much tapped out. Unless you're in that northern atmospheric river path, which I showed, which kind of goes back to your question, Amy. And those kind of sneak up into here and it penetrates a little further. So northern Montana gets about the same amount of moisture out of ARs as we do. But then there's this kind of dark patch here. And then not quite as fine a resolution, but just state by state, you can see Wyoming in general and Colorado in general really don't get much of their annual precip. These lighter blue colors are down less than 25% from atmospheric rivers. One holdout from that would be southwestern Colorado, which does get atmospheric rivers that sneak in this pathway here south of the Sierras, but it's not quite high enough resolution to pick that out in this graph.
All right, so we have another question from Russell. Do high pressure domes affect atmospheric rivers? And why do high pressure domes lock in over central Idaho?
Yeah, so that would probably be best explained from back to our, let me find this slide here. So to your question of why do high pressure domes kind of lock in over central Idaho, I think that's kind of maybe a recency bias. And I think all of us kind of have that in our minds because we've seen so many of those blocking high pressures lately. It's not that it happens all the time, but it is a trademark of a La Nina winter, which when we have these cold pools of water here and this air coming down, that's what creates a high pressure. So subsiding air creates more air in this column, which is what high pressure is more air in a column and less air in a column here, more weight of a heavier column of air. And as that air comes down, it compresses and warms and dries. So those blocking high pressures shown kind of right here, set up over that general area where there's sinking air, and that pushes the storm track to our north. So that's kind of that dome that we get. And what was the beginning of that question? It was, do high pressure domes affect atmospheric rivers? So they do. So what has to happen is this blocking high pressure has to weaken slightly, or the jet stream has to kind of dip down a little bit more, because we need a low pressure storm to sweep down into this area, which you can see in that one that we got in October right here. We have a little bit of a high pressure at the end of that loop, but then here comes this low pressure system and it swoops down. And as it intensifies, it really ramps up as it draws that moisture in. So you need a low pressure system to break through that high pressure dome. And once you do that, it has the potential to tap into moisture and become an atmospheric river.
All right, if anyone that asked questions wants any follow-up, feel free to type those into the Q&A box as well. And it looks like that's all of our questions right now. If anyone else that's on wants to get Ethan while we've got him, feel free to type your questions away or hit that raise hand button. We'll stick around for a few more minutes on here if you've got burning questions.
One interesting fact that I can fill in with, again, from Mike Houston at the National Weather Service, is we're in a back-to-back La Nina year, which is something that we haven't had very many of. And so he was kind of interested into seeing what back-to-back La Nina years tend to produce. And there's only eight samples to look back on. But in the Bigwood Basin, the second of a back-to-back La Nina ranged from 47% less snow to 2% more snow. But what the average was about 18% less snow, which is roughly a foot less snow than normal. But again, that's an average. And given how dry it was last year, I doubt highly that we will have less snow than last year. It would be very, very, very surprising. But my guess is that will fall on the lower side of average based on the fact that every other second of a back-to-back La Nina year tended to be relatively dry.
Well, shucks.
Yeah, sorry to.
Let's all hope for the best with that one. Well, Ethan, doesn't look like we have any more questions coming in yet. But we can, as I share what our upcoming education events are, we'll leave a few more minutes for people to type final questions in before we let you go. So if folks are thinking of something to ask Ethan, feel free to type that in. And I'll just share what we have coming up for the next few weeks. So we hope that you join us at the 5th Annual Homegrown Film Festival that's coming up on Saturday, December 4th. There's a showing at 5 p.m. and 8:30 p.m. at the Arduous, and that features local filmmakers and athletes, both amateur and professionals. And from the raffle, we've got some amazing prizes that I would hope to win. So I imagine that most of you would love to get a chance at winning some of those prizes, and all of the proceeds benefit the Avalanche Center. You can find more info on that at thearduous.com, homegrownfilmfest.com, or on our social media at Sawtooth Avi. The next Digging Deeper presentation is on December 15th. We're running these every 2 weeks, and that one will be with Chris Lundy, and he's going to dive into the question, are we taking too much risk? Something we should all probably ponder. And so Chris is going to give us some expertise on that, December 15th. And then for December 8th, we have a presentation that is good for people who would like a refresher on avalanches, or if you know of folks who are newer to avalanches, this is a great overview. It's Intro to Avalanches. It'll be a 2-hour presentation on Zoom. That will be with myself. And then on the Saturday, December 11th, following that presentation will be a field day in the mountains with some of our instructors. And you have to go to the presentation in order to go to the field day. So spread the word on those events. And I think that wraps it up for December. We'll have our newsletter coming out with more events. And it looks like we don't have any other questions coming in. So just like to send a huge thank you to everyone who participated with us tonight. And we're really looking forward to the day we can do these in person. And a huge thank you to everyone at the Friends of the Sawtooth Avalanche Center with their fundraising efforts. And a big thank you to Ethan for sharing his expertise with us. And we're looking forward to those daily forecasts once it does snow a little bit more. So thank you so much, Ethan.
You bet. Thanks, everybody.
All right, we'll see you next time.